Today we're going to talk about more radicals. It's still Unit 5, yep. Yesterday we talked about how to simplify them, whether they have just values or variables in them. The goal yesterday was finding those hidden perfect squares. They allowed us to simplify our answers, so on and so forth. Today we're going at it from a different approach. Now we're going to see what happens when we have what are called radical equations. Now, there is some confusion there. Part of that confusion is that just simply having a radical in an equation does not necessarily make it a radical equation. And the reason for that is not only do you have to have the radical sign, but the variable that you're solving for must be contained within it. So I have two examples here for you. They look very similar. In fact, they have mostly the same pieces, but the difference is the linear equation, notice the variable is not inside the radical sign, which means that you could technically solve this using the same steps we've used before. Now, it would look a little bit strange, but if you think about it, could your calculator give you an approximate value for the square root of 3? It would be a decimal. It'd be like 1.8, 1.9-ish. If you want to check, go for it. But it would be an approximate value, which means like any other value, technically I could add it to both sides. 1.73. That's kind of close. But I could add that square root of 3 to both sides. That would get rid of it from the left-hand side, leaving x by itself. And you said about 1.73. So actually, let me say approximately 8.73, because 7 plus the 1.73 would give you approximately 8.73. This one is very specifically solvable based off of what we've done in the past. Ultimately, the goal here is still get that variable by itself. It's not trapped within anything else. So it's very straightforward.
No, that's really simplistic. Can you write on the side what you did 7 plus?
Yeah.
You did 7 plus 3.
Well, all we did here technically is, thanks to Harmony, she said the square root of 3 is approximately 1.73.
So we just added that to 7.
So we just added that to 7. Because the ultimate goal there, if you want to see the guideline here, all we're doing is getting that variable by itself. X originally had square root of 3 being subtracted from it. We do the opposite. We add it. But since the square root of 3 doesn't quite look like the other numbers we're accustomed to, we take its approximate value, 1.73, add it to 7, and we get an approximate answer of 8.73. Now, it's not exact. In order to work with exact, you'll learn more of that in Algebra 2, how to have values that have both a constant part and a radical piece, which still contains then the exact value. But for today, really our ultimate goal is to introduce a new type of equation, which follows its own slightly different set of rules. And what's interesting about it is with a radical equation, there is potential that it could turn into different types of equations, depending on what type of radical equation it starts out with. So I'm going to show you the second one over here. Right now, the problem is that if I were to try to solve the radical equation, which has mostly the same parts, the difference being that the x is inside the square root, I can't move these two pieces because think of them as being buried within the problem. They are hidden right now inside the square root, and until I take care of the square root or get it out of the way, I can't move the x, not that I would want to, I can't move the -3. I can't really do anything with that problem using the skills we've used in the past with linear equations. So as a result, we have to have a slightly different approach, which is why I've given you steps for solving radical equations. So once you've identified that an equation is in fact radical, meaning that the variable is inside your radical sign, First thing you want to do is isolate the radical on one side. So get it by itself. In other words, if it's not inside the radical, it needs to move. It needs to get to the other side of that equal sign. Once you've got the radical isolated, we're going to square both sides of the equation entirely, which means we're going to take the entire left-hand side and raise it to a power of 2, and the entire right-hand side, raise it to a power of 2. But I want to draw your attention to this little note here. This may create a quadratic equation. Now, what that means is it'll be a degree of 2, and that will then change our approach again. So we'll shift from taking it from a radical equation to a quadratic equation, which from unit 4, we had a list of steps that we could use to solve it. So the steps will actually evolve depending on how the problem changes in this step. Now, if it turns into a linear problem, then we don't have to worry too much about it then. All we'll have to do then is get the variable by itself. So that's why step 3 is kind of open-ended. It says solve the equation. I'm going to highlight it. It says accordingly. What I mean by accordingly is if it is quadratic, if you refer back to earlier notes, quadratic equations, we got it set equal to 0. Typically, we tried factoring, set each of those factors equal to 0, and usually get 2 answers. If we get a linear equation, meaning there is no power of 2 still remaining, well, then we just get the variable by itself. Now that means linear equation, so we did parentheses, like terms, variable on both sides, get the variable by itself. So it could be quadratic, it could be linear. There's other scenarios out there which we'll try to avoid. These will be the most common. It'll either turn quadratic or it'll either turn linear. And we're going to consider both scenarios. So just to practice these steps, we have a problem here solving the radical equation using the steps listed above. First off, is this a radical equation?
Yes.
How can you tell? So both of you together. So there is a radical sign, but a little deeper than that, the variable is inside that radical sign.
Because that linear equation was it the one on top?
Correct. The one up above, yeah, that's a good question. The one up above was not a radical equation because the variable was not inside it. So even though a radical was involved, it was not a radical equation. Well, that's a common mishap there. But this one, the variable is buried right there inside the radical sign. So this one is in fact a radical equation. Now, just for the sake of trying to be organized here, I'm going to try to approximate how much space I'll need. Step 1, now that we've identified it as a radical equation, what do we need to do first? Isolate the radical on the one side. Currently, it is on the right-hand side. Is there anything else on the right-hand side that is not contained within the radical?
+5.
That +5.
So we want it to just be, so in other equations, like the past, the y is supposed to be, so we're moving it, so we say that, what are we looking for? What are we trying to?
Our goal ultimately is to get the variable by itself. The reason why we have to take a slightly different approach here is because the variable is buried inside the radical. So until I get rid of the radical sign, which I have to do in a particular order, until I get rid of it, I can't do anything to get it by itself.
But it's okay if like it's something equals that radical. Actually, never mind. I'm thinking which is best.
It could be, I think you're just thinking ahead, which is fine. It could be set equal to anything.
Well, I shouldn't be, 'cause I have no idea what this is. So.
Well, it can look a variety of different ways. And this one's going to be a little bit of an easier one. The ones on the back we're going to look at are a little bit more in depth, but we're going to consider, I mean, obviously we're going to see some examples of both. But for this one, you guys are telling me that +5 is not part of the radical. How can I make that disappear from the right? Subtract it. So I'm going to subtract it here on the right. But as with any equation, whatever you do on one side, you have to do the exact same to the other. So on the left-hand side, we've got 9, take away 5, which leaves me with 4. equals, we still have the square root of 15x plus 1. But then the 5, take away 5 is now gone. It's been removed from that side of the equation. So I believe step 1 is done. And if you want to make a little mental note here off to the side, this step was to isolate the radical. Actually, if I wanted to make this extra pretty, technically I'm going to have to shift this up a little bit. Right there. After the radical's been isolated, what's the second step say? Square both sides. Now, does anyone have an idea why specifically are we squaring both sides? Well, look, Harmony, I didn't catch what you said. The hidden two. Okay. Interesting to call back to yesterday. Technically, if you remember, radicals have an index. And it just so happens that this index is a 2, which likes to hide because of it being a square root.
So is it always a 2?
So if it's anything other than a 2, you'll see it. If you don't see it, you assume it's a 2. Now, if you think about it, listen to what it's called in and of itself. This right now is the square root. Well, the opposite of square rooting something is squaring it. The opposite of squaring something is square rooting it. We're about to use just another inverse set of operations that we are now newly introducing. Way back at the beginning of this term, if something was being added, we subtracted, and vice versa. If something was being multiplied, we divided, and vice versa. Well, now, if something's being square rooted, we can square it. But here's where you have to be careful. We are squaring the entire, the entire right-hand side, which means I also have to square the entire left-hand side. A little crowded there. That was poor planning on my part.
I might take a minute to rewrite it.
That's okay. So while he's rewriting his here, I'm going to make a note that this step, we are squaring both sides to get rid, I'll throw that in air quotes because it's not so much that we're getting rid of it, we're just kind of undoing it to get rid of the radical. Now, I'm going to start on the easy side. 4 squared. What is 4 squared? Not square root of 4. 4 squared gives me a 16. On the right, guess what that squared, that exponent of 2 is going to do to the square root? Well, when you add something that's being subtracted, what do? They cancel out. Back here when the 5 was being added, we subtracted it, it was gone. Well, guess what? If you have something being square rooted and then you square it, guess what happens? Execution. It's gone. It's sure, if you want to call it being executed, that's fine. But because a square root and squaring something are inverse operations, they cancel each other out. And guess what's left behind? Well, I'll give you a clue. Well, actually, I'll just give you the answer. It's everything inside.
So nothing changed.
I wouldn't say nothing changed.
Well, I mean, like the numbers themselves still.
Right. So that square, think of it this way. They are wrapped in this radical sign. And all that happened when we squared it, it peeled away that outer layer. That radical is now gone. We've thrown it in the trash. We've gotten rid of it. All that's left is what was contained within. I just now got that out. I didn't actually do anything to it. I didn't touch anything. 15x plus 1 is now free to move about as it wishes.
So we can actually do any math involving the two.
Well, we didn't touch it yet because they were, like I said, we couldn't mess with the 15x plus 1 until we got the radical out of the way.
So we're just rewriting that. That's just.
Sort of, yes. Now, my last little note I'm going to jot down here is that this equation is now linear. So our goal, so we need to get the variable by itself. So I was tying these to different parts here. Well, hopefully we recall how to solve linear equations. Are there any parentheses? No. Like terms?
116. Wait, no, they're not.
They're not on the same side. Good catch. So they're not like terms as the variable on both sides.
No.
No. So really all that leaves me to do is to get that variable by itself, starting with moving what? The 1. How would you move it? So we're going to subtract 1 from both sides. So 16 take away 1 gives me 15. 15x comes down. 1 minus 1 is gone. What's left to move? The 15 off of the x. It's being multiplied, so we're going to divide both sides by 15. 15 divided by 15 is 1. And just because we started unit 1 with it, let's make sure we keep our habits consistent. I'm going to go ahead and rewrite my final solution as x equals 1. I'm also, the picky side of me is going to go back and make sure that this little guideline stays true all the way through the problem. So in reality, the only thing that's new today is at the beginning. In the past, we usually added steps at the end. This time, we're sliding in some new steps at the beginning. When the equation starts off as radical, we get the radical by itself. We square both sides, and what we're left with will be one of the old types of equations that we've encountered several times in the past. Now, odds are it'll either be linear, as this one was, or it'll be quadratic, which we'll see some examples of that here in just a moment.
So will it usually turn into a linear equation? Said, I think what not messed me up, but like I remember that it might create a quadratic equation, and I was like, oh, okay, so this is just going to be one of the easy ones because it didn't do that.
So if it's linear, I don't want to say easier, but I would say that it may feel easier to most people.
Because we're used to.
Yeah, it's certainly one we've solved most often. Quadratic is still fairly new. It's probably the newer of the ones we've learned, but maybe it's also still the freshest in our mind. I don't know. So I don't want to say it'll necessarily be the easiest, but each person will be different. So there we have our first radical equation solved out. Turns out that the answer is 1. And if I wanted to do a quick mental check, imagine what happens if I were to drop 1 right here where the x was. 15 times 1 is 15. 15 plus 1, 16. Take the square root of 16. 4. 4 plus 5, 9. Boom, it works. It would end up in a true statement. So we found the one and only value that would work in this scenario. I can bring it back for anyone who still needs to write it down. Want to make sure we have time to do a few more here. So I try to cover all the bases here with some of the more common scenarios you may encounter. Guess here about how much space I'm going to need again. So just to run through our process, is this a radical equation?
Yes.
How can you tell?
Variables.
The variable is inside the radical. Good. So our steps are going to apply here. Step one, isolate the radical. Is there anything that's not contained within the radical that should move? The -3? Okay. Ah,
No.
I fooled you.
No.
Is that -3 being, is it being subtracted? No. How's it related to the radical? It is being multiplied.
So it looks like you said a radical is still a grouping symbol, so it's technically.
It looks like it's wanting to be distributed, but because it's not parentheses, it couldn't, which is why it's so important to get it out of the way. But it does behave similar to parentheses in the sense that it is still being multiplied. So if -3 is being multiplied with the radical, the only way we can get rid of it is if we divide this entire side by -3, which means we divide the entire left-hand side by -3 as well. So on the left, -24 divided by -3 is going to give us a +8. Bring down my equal sign. -3 divided by -3 on the right, those are going to simplify to a +1, which allows us to hide it, which then makes the radical itself appear to be isolated. So we still have the square root of x plus 8. So step one is done. The radical has now been isolated. What is step two? Square both sides. And this is the reason why we're doing this again, is to make the radical go away. The opposite of squaring something is square rooting it. So we want the radical to disappear. So I'm going to square the entire right-hand side. But as with any equation, whatever you do on one side, you have to do the exact same to the other. So I'm also going to square the left-hand side. I'm going to start with the easier of the two. What is 8 squared? 64. On the right-hand side, what is the square root and the square going to do?
Just rewrite the x.
Yep, just rewrite the x plus 8. The square root and the squared, or the exponent of 2, eliminate each other. They're opposites, so they cancel each other out, leaving us with just x plus 8. Now, what type of equation have I now created? It is linear again. How do I know it's not quadratic?
Because there's no words.
Well, I think I know what you're getting. No little 2 on top. No exponent of 2. So this one is in fact linear. So we run through our linear steps, no parentheses, no like terms. The variable is not on both sides. All I really need to do then is get the variable by itself. So I would subtract the 8. What did you say it was? 56. So I get 56 equals x. And again, so we're remaining consistent. We would then just rewrite that as x equals 56. We could check that again fairly quickly if you were to imagine. If you were to drop that 56 right back in where the x was, what's 56 plus 8? 64. What's the square root of 64? 8. What's 8 times -3? -24. It would result in a true statement. So instead of sitting here and trying to pick out numbers off the top of our head to see what would work, what wouldn't work, we cut out all the guessing and we simply got straight to the answer, the one and only answer. Cool. Next one. Uh-oh, this looks kind of unique. What do I mean?
It's got 2 radical signs.
It has 2 radical signs. Now, before Right, both on different sides, so pretty strange, but let me ask you this. Let's again ask ourselves the same questions we've been asking. Is it a radical equation? Yes. How can you tell?
In both radical signs, the variable is inside.
So in both, there's a variable inside. Now, ultimately, does it have to be, would both radicals have to have the variable inside, or is it good enough to have just one variable inside?
Just one.
Yeah. So long as at least one variable is inside one of the radicals, that is enough to say, yep, this is a radical equation. We're going to pursue the steps we've introduced today. So step one, isolate the radical. Kind of a head scratcher at first until if I ask you this, is the radical on the left, is there anything outside that radical? A 1, but thankfully ones like to hide. So for our purposes, I'm going to pretend like it's not there. On the right-hand side, same situation. So technically, could one argue that both of them in their own regards are isolated? Sure. So although it's a little bit unique, the radicals still have been isolated, which means I'm ready to jump into step 2, which is to do what? To be isolated means that there are no components outside the radical. This is it.
They're simplified into one final piece.
Yep, nothing outside. There's nothing being multiplied, nothing being added or subtracted. Just you have the radical, anything inside of it is part of that radical. What's step 2? Square, just what? One side, both sides? Both sides. And that shouldn't surprise us too much because whatever you do to one side, you have to do to both sides. So nothing we had to do to isolate it. So we jump into squaring both sides. So I'm going to square the left-hand side. I'm going to square the right-hand side. Now, as in the past, what happens when you square a square root? It cancels out. So what is remaining on the left-hand side? 2n plus 3. And what's remaining on the right-hand side? 3n. So although it started off a bit unique, the steps still led us to this scenario. What type of equation is this? Still linear. Still don't see a power of 2 anywhere, so we're still working linear. So we're going to run through our steps. Are there any parentheses? No. Like terms? Got yourself. Jay said yes at first.
Because like all high school, whenever they'd ask us that, as long as there were two that had the same variable or whatever, the answer was yes.
Well, I like to think that my definition is a little bit more helpful because it doesn't allow you to accidentally combine things before you're ready. So Toby, just to bring you up to speed with Jay, why would the 2n and 3n not be like terms?
Because they're not on the same side.
They're not on the same side. So as much as I want to combine them right now, I can't yet. But fortunately, after like terms, I then ask myself, is the variable on both sides? And in this case, it is. Typically, which one would we move? We could move the, well, careful. Are you talking about just the regular 3?
No, 3n.
The 3n? I could.
I kind of caught myself because I know it equals 0.
Which I don't want you to be afraid of. If it equaled 0 and then you still got the variable by itself, it would still work out.
It could be easier on the eye to write the 2n over by the 3n on the side. That way they both be on the same side.
I would agree. I personally would move the 2n, not only because it would avoid having a side equal 0 for just a moment, but usually I try to move the smaller of the two. And the reasoning for me behind that, it avoids more negatives than what I want to deal with. Because if anything is going to trip anyone up, it's usually a negative sign. So how would we move the 2n?
Subtract it.
Okay, so I'm going to subtract 2n from the left as well as the right. So 2n minus 2n is gone from the left-hand side, leaving me with a positive 3. On the right-hand side, we're lucky. 3n, take away 2n, just leaves me with n. Now, if you want to write 1n, you're not wrong. You would either divide both sides by 1, which would really change nothing, or you would just hide the 1. It's entirely up to you. But what did I end up with then? N equals 3. Pause for a moment while my minor case of OCD kicks in. Good. So again, even if we were to consider this one, imagine if we drop the 3 in for all the n's in this problem. On the left-hand side, 3 times 2, 6, plus the 3, 9. What's the square root of 9? 3. So we'd get a 3 on this side. On the right-hand side, 3 times 3 is 9. Square root of 9 is also 3. We would end up with a true statement, 3 equals 3. So this is the one and only value that we could drop in for all the variables in and still have a balanced true equation. Now, so far, all these equations, once we've addressed them for being radical, what have they all turned into so far? They've all turned linear. And that, Jay, you wanted to say it was an easier example. I would say now, probably, because when it comes to quadratics, which we're going to consider here, we introduce this new concept of the potential of there being what's called an extraneous solution. Now, extraneous sounds like a scary number or a scary word right there, extraneous. So extraneous solutions. So it says occasionally when using steps to solve radical equations, the equations can become quadratic. That's okay. We know how to solve quadratic equations. But what we probably recall is when we solve quadratic equations, we typically ended up with 2 unique solutions. Now, the problem with that is, so far when we've been finding one solution from the linear equations, that one solution usually worked. When it turns quadratic, unfortunately, there's no guarantee that both solutions will in fact result in a true statement. So when this happens, what we usually do is we refer one of the 2 solutions can in fact be extraneous. Now, extraneous, if you hate that word, you can think of it as just extra. It's an extra solution we find through our process, but when we go back to evaluate it in the original problem, turns out it didn't actually work. So in these situations, it is very important to check both of your solutions in the original radical equation. So I'm going to highlight a couple pieces here. Check both your solutions in the original radical equation. And I'm also going to highlight that it says that the equation can become quadratic. So I'm kind of giving you a shortcut here. Used to be, I'd have students check all of their answers with radical equations. But linear equations usually work out very kindly. It's the quadratics you have to watch out for. So you only have to check for extraneous solutions if, in your process of solving it, the equation turns quadratic. So I'm going to show you what that process looks like. What would have to happen in order for it to become quadratic? So, still following the same steps. I'll try to, I think this will give me enough space. First question usually has been, is this a radical equation? How can you tell?
Yeah, at least one of the variables inside.
At least, and I like the way that you specify that, at least one of the variables is inside the radical. Doesn't matter that, it doesn't really matter that this one is not. All we need is at least one of the variables trapped within. So it is radical. So we're going to apply our steps. Step 1, isolate the radical. This one happens to be on the right-hand side. Is there anything else on the right-hand side that needs to move? I'm seeing some no's.
It's already one.
It's already one whole piece. The whole radical is already isolated on the right-hand side. So step 1 is essentially completed for us. So what's step 2? Square both sides. Now here's where it gets a bit unique. In the past, when we squared both sides, most of them were usually just a value on the other side, which was really nice because it's very easy to square just a number. This one, what's on the left-hand side? Sorry? A variable, not only a variable, but also a number. We have vocabulary for this. What do you call two-term? We have a binomial. This is going to be rather unique. So let's see it. So we're going to square the right-hand side. We already know what that's going to do. But on the left-hand side, this is where we're going to have to be a little bit careful. So I'm going to do the right-hand side first because that's more familiar with today's topic. What is the square and the square root going to do? Cancel out, leaving us with, on the right-hand side, 7a plus 42. So that part is just like the rest. On the left, however, I am squaring a binomial. Now, depending on your comfort level, there's going to be some different things here that could affect what your instincts are wanting you to do. Good. So in case you didn't catch what Jay said, on the right-hand side, the reason why we didn't worry too much about it, because we put the square over a square root, they just canceled each other out. On the left, though, is there a square root there as well? No. So we have to actually use the exponent of 2. Now, initially, the first reaction a lot of students have is just go ahead and square both terms. You got to be careful because technically an exponent of 2 tells you to do what with its base? Multiply it with itself twice. What is my base here? It's not 6. It's not a. It's not 1. It's a binomial. A plus 6 is the base. So just like any other squared scenario, I'm going to have to multiply the base a plus 6 with itself twice. Oops, not 2. So in case you're still confused, if I said, what's 5 squared? 25. How'd you get that? 5 times 5. What's 7 squared? 49. How'd you get that? 7 times 7. Well, what's a plus 6 squared? Well, we don't know yet, but we do know that it's going to be a plus 6 times a plus 6. Sorry? Close. So whatever the exponent does is it tells you how many of those bases to write. In this case, on the left, we have an exponent of 2. We have a base of a plus 6. The parentheses tell me that I have to consider the entire thing as the base, which means I have 2 of those binomials multiplied together. If it was a power of 3, I'd have 3 of those binomials. If it was a power of 10, I'd have 10 of the same binomial multiplied together. Now, Harmony said 36 and a squared. We got 2 of the 3 terms, but what you have forgotten is that when you multiply 2 binomials together, well, let's see. If I go all the way back, this is why I usually suggest keeping your notes all the way back to polynomial operations, multiplication, binomial times a binomial. This is where we'll either use FOIL, if you've learned that in the past, or you can set up a box like I introduced. So it's not enough just to multiply the first and last term. You actually have to show that entire multiplication. So off to the side here, oops. I'm going to set up a little box.
I actually have no idea. I never use FOIL. That's just how the word. So what are the rules for that?
Well, if you like the box, I would say don't worry yourself with FOIL. It does the exact same thing. It's just a different way to represent a binomial times a binomial. The reason why I don't do FOIL anymore myself is because that acronym does not allow you to grow to fit larger problems. It only works for binomial times binomial.
Well, I mean, the rule, like, how do we write it out, like the A's and 6?
Oh, well, in the box, I would label my rows with one binomial, a positive 6, and my columns with the other binomial, a and positive 6. And then one at a time to fill each square, I just multiply the row by column. So starting in the top left corner, a times a squared. Going to the right, a times 6. Next row, 6 times a. And the last one, 6 times 6. Now here's what I liked about the box. That diagonal usually contained like terms. So when I go to write this entire thing out here on the left side of my equation, I'm going to have a squared. What are the 6 a's going to combine to make? Plus 12a. Plus 36.
3 6s probably 2.
3 6s?
Yeah, where'd you get the 3 6s?
Only got 2 6s. Here's one binomial, a plus 6. Here's the other a plus 6. These 6s in here are just results of multiplying. A times 6 or 6 times a.
So what was the point of multiplying the first one by that is 6 and 6?
So the box just helps me organize my work. The result is this trinomial. Now you'll notice if you had just distributed, you would have gotten, like I mentioned to Harmony, you would have gotten 2 of the 3 terms. We have the a squared, we have the 36. You would have completely overlooked the 12a though. And that is extremely important not to lose because obviously it would change the problem. So let's make our notes a little bit more useful. So this, I'll make a note here that this was for multiplying binomials.
Oh, did you just add the
Sorry?
Did you just add those diagonally?
Yeah, the 6a and 6a would be like terms.
Okay.
Because if you were to write this out in the old school foiling, you would have had a squared plus 6a plus 6a plus 36.
Okay, so
The
does it
6a
matter-
and 6a would makes the 12a.
Does it matter if we write the a squared first, or like how did we?
Well, that's a good question.
Use of how like we transferred that.
So-
to keep it organized.
Knowing that this equation is turning into a quadratic equation, in the past, I recommended always writing in descending order. So that's why I started with the highest power, then the next highest power, then the lowest power. So this one is obviously very different than the previous ones because this one is not linear, it's quadratic. And how can I tell it's quadratic? It's got a power of 2, and conveniently for us, it is also already in descending order. So now I have to follow a new set of rules. This is no longer radical. It didn't turn linear. It turned quadratic. And when I'm solving quadratic equations, the first thing I want to do is to have that equation equal what? 0. So which side would you like to start moving things away?
Right.
I would agree. I'd start moving things off the right-hand side. How would you make that 7a disappear?
Subtract it from 12A.
Good. So there is conveniently a like term to subtract it from on the left. What else would you move?
But I thought we couldn't move that from on the same side.
There, you can't combine them,
Oh,
but you can move them.
that's just another word says subtract.
Yes. What else would I move here? The 42 from the 36. How would you move the 42? So we've got a lot of changes here in this one step. I'm going to do the easy side first. The right-hand side, 7a take away 7a is 0. 42, take away 42 is also 0, which means that this equation, as I like, is going to equal 0. On the left, did we touch the a squared? No. So still have an a squared. 12a take away 7a will give us 5a. 36 take away 42, -6. Looking good so far. We've already come so far, it's almost easy to forget that this one started off as a radical equation. And for my purposes, I'm still going to pretend it's not a radical equation, because what I'm looking at is that it's quadratic. So if it helps, ignore everything else. If this was the equation we were solving, it's already set equal to 0. After setting it equal to 0, what do we do next?
We're not adding that 6, are we?
No, because that would make it not equal to 0 anymore. We spent a whole long time doing this, all kinds of different ways to, starts with the letter F, factor. I want to try to factor the left-hand side. Now, when you're factoring, what do you always check for first? Is there one here?
No.
No. So then I would consider the asterisk method. So I'm going to make a note here that now we are in the process of factoring. And for factoring, you said the asterisk. So what's my A? 1. My B is 5. And my C is a -6. Make my notes extra pretty here today. So we say, okay, we're factoring. So I'm set up my asterisk. We already considered the greatest common factor. On top, we'll have A times C. So we have 1 times -6, which is -6. A on either side are 1s. B on the bottom is 5. So I want two numbers that multiply to equal -6 that also add to equal +5. -1, +6. So let's try it out. -1 times 6 is -6. -1 plus 6, +5. Sounds good. So we get these two special pairs. Do either of them simplify? No. And remember, these are really just serving the purpose of giving us two binomials. So even though some of them you may think, well, that one on the left could become -1, they're not fractions. They're giving us binomials. So I'm still going to have 1 over -1 and 1 over 6.
I remember like last week or something, we were working on them. I pointed that out, then I realized no. But then like on another example, we did one and the answer was like 7 over 7 and you changed it into 1 over 1.
I simplified it.
Yeah.
So I still left the two terms, the two pieces, but I didn't get rid of it entirely. So at this point, we bring back our variable, which in this case is the letter A, before writing the top terms in front of the bottom terms. So what two binomials do I get?
A
1A minus 1 and
A plus 6.
1A plus 6. Goodness, what a process. We're not even done yet.
So we only have so much space.
We're doing all right for space. So at this point, let me adjust my notes here slightly so it looks extra pretty. So at this point, once we had it factored and it was set equal to 0, it was here where we said, okay, this is the prime candidate for the zero product property. Because if you have a product set equal to 0, then at least one of those parts of the product themselves must equal 0. So either A minus 1 equals 0, or a plus 6 equals 0. Goodness. How would you solve that first one?
Also,
Plus 1 to both sides. So you get a equals 1. How would you solve the second one? Subtract 6. You get a equals -6. Now, for a moment, I'm going to go ahead and box both of these in so that I can find them. But what do I have to remember could possibly happen? Was this a quadratic equation the entire time? No. What did it start off as? It started off as radical, which means even though I found 2 solutions through this process, there's a high probability that one of them is what? False, or there was a word for it. Extraneous or extra. One of these could quite possibly be an extra solution, and there's only one way to tell. Plug it into the original radical equation. Here's the reason why I specify that we had to plug it into the original radical equation. I know these 2 solutions work for the quadratic equation, but it wasn't a quadratic equation I was initially solving. I need to know, does it simplify or does it satisfy the radical equation? So off to the side here, hold on, let me set up my workspace here very quickly, always thinking ahead. Make sure I save enough space for the second problem. Off to the right here, I'm going to make sure that we check for an extraneous solution. So we're going to have 2 sets of work. So the original, I have a copy here so I can see it. So we're using the original radical equation. I'm going to check a plus 1 first. So we'll have, actually, let me jot it down over here so we can see it. So a plus 6 equals the square root of 7a plus 42. So let me adjust this here. Whoops. A lot of students think, why does he spend so much time doing his notes like this? Well, because if I'm going to look back at them later, what's the point of doing them if I'm not going to do them well? So each of these solutions, we're going to plug into that original radical equation, starting with a equaling 1. So I would get, I'm going to use parentheses to show the replacement. I'm going to get 1 plus 6 equals the square root of 7 times 1 plus 42. Now, I don't want to go crazy here and get things flipped around. On the left-hand side, is there that much we can do? Or can we just add? The parentheses, are they really doing much on the left-hand side? No. Just showing me that, hey, yep, this was a replacement. So really, for our purposes, can I just go ahead and do 1 plus 6?
Yeah.
Yep, that'll mean the left-hand side I don't have to worry about until I finish this problem. On the right-hand side, I'm inside the radical. I'm going to have to do those parentheses first. What's 7 times 1? 7. So I have 7 plus 42. What's 7 plus 42? 49. So I end up with the square root of 49. And what's the square root of 49? 7. So I end up with the statement that 7 equals 7. Is that true? Yes. Actually, let me just write the word true. So let me ask you this. Is 1 a solution? Yep. Now that means there's potential that -6 may not be a solution. But there's only one way to tell, and that is to drop it into this problem. So same thing. -6 plus 6 equals the square root of 7 times a -6 plus 42. On the left-hand side, again, the parentheses really are just saying, hey, there was a replacement here. What's -6 plus 6? 0. Okay. On the right-hand side, what's 7 times -6? -42. What's -42 plus 42? 0. And what's the square root of 0? 0. Is this a true statement?
Yeah.
Well, wouldn't you know it? Did both of these solutions work?
Yeah.
So it just so happens that this one has 2 solutions, 1 and -6. Now, was that guaranteed? No. In fact, it was very possible that one of those didn't work. What a process, right? How could he make me do so much work? Ugh. So we had to solve it as a radical equation. It turned quadratic. So we said, okay, let's solve it as a quadratic equation. Went through that process, ended up with 2 solutions. It wasn't enough to say, yep, these are my 2 answers. We had to then go back to the radical equation and check. Now, good news is, if you get comfortable with these today, this is an entire lesson in Algebra 2. So if you want to think about it, this is an Algebra 2 lesson today. But in reality, it used very few new steps. All right. We got time for the last one. We're doing really well for time. Again, if at any point you need to go back and see any of this, I'll have this posted. I'll also have the video posted as well. You're welcome to revisit that as much as you need to. But let me go ahead and initially set up my problem here. Is this last one a radical equation?
Yes.
How can you tell?
At least one of the variables is inside the.
At least one of the variables is inside the radical. Awesome. So we're going to go into radical mode. First step, isolate the radical. Already isolated. There's nothing else on the left-hand side here that is not already inside the radical. So step 2 is to do what?
Square both sides.
Square both sides. So I'm going to square the left-hand side entirely and square the right-hand side entirely. On the left this time, not a whole lot's going to happen. What's that square going to do to the square root? Cancel out, leaving me with 5p plus 21. On the right-hand side, we're squaring a binomial. So that is telling me that I am multiplying the binomial p plus 3 with itself twice. Yep. So p plus 3 times p plus 3. So off to the side here, set up my little box. Ooh. Same 2 binomials, so we'll have P and 3 labeling our rows, P and 3 labeling our columns. I like to start in the top left corner. What's P times P? P squared. Going to the right, P times 3, P3 or 3P. 3 times P, another 3P, and then 3 times 3, 9. And similar to the earlier one, check that diagonal. You're going to see some like terms there. That's pretty convenient. So when I go to write this out as a nice clean trinomial, the right-hand side of my equation now becomes P squared plus 6P plus 9. Bring down the 5P plus 21 because we haven't done anything with those yet. And this equation now has become what?
One.
You had it. It's now quadratic. So we went from radical to quadratic. We changed our steps now. In order to solve a quadratic equation, what is the first thing you want to happen? Before we factor,
You need a 0 on one side.
we need a 0 on one side. So which side would you like to start moving things? The left-hand side? What would you move?
Negative
So
21.
this doesn't have to be in some.
Subtract 21.
Well, technically, so yes, Harmony.
Because I would think that the P2 would be first for this.
Well, technically on its own side, it is first. So it is on descending, it is in descending order. It's just on the other side of the equation this time, which is okay.
Okay.
Harmony, you said subtract the 21
From the 9.
from the 9. What else could you move?
The 5.
The 5P? So subtract the 5P from the 6P. So on the left-hand side, 5P take away 5P is 0. 21 take away 21 is also 0. What do we have now on the left-hand side?
P squared.
0.
Left-hand side. 0. On the right-hand side, you said P squared. 6P take away 5P. Positive 1. So 1P. And then 9 take away 21. Negative 12. Good. So it's set equal to 0. Now can we factor?
Yeah.
What do you always check for first?
There's one.
Is there one here? Not this time. So what do we try next? It's a quadratic trinomial. We use the asterisk method. So in this case, what's my A? It's in front of it. 1. What's my B?
1.
Also 1. What's my C?
Negative 12.
It's a negative 12. I'm setting up my asterisk. A times C on top, we're going to have 1 times a negative 12, which is negative 12. A on either side, which are 1s, B on the bottom, also 1. So two numbers that multiply to equal negative 12 that also add to equal positive 1.
So 1 minus 12.
Sorry,
1 minus 12.
1 minus 12?
I hit the word.
Well, what would 1 minus 12 be? A negative 11. I want a positive 1.
Negative 3 and 4.
Negative 3, positive 4?
Yeah.
So negative 3 times positive 4 is negative 12. Negative 3 plus 4 is a positive 1. So it sounds like we've got them. Looking at these two pairs, do either of them simplify any further? Nope. So we have enough information now to write out our binomials. So 1 over negative 3, bring back the variable p. And 1 over 4, bring back the variable p. Writing the tops before the bottoms. What two binomials do we get? 1p minus 3,
And 2 plus 4.
p plus 4. Still equal to 0. And because I overestimated how much space I needed. Now that it's factored and set equal to 0, now I can say, this is a zero product property situation. If you have a product set equal to 0, at least one of those parts of that product themselves must be 0.
One P minus two equals zero.
So either 1p minus 3 equals 0, or p plus 4 equals 0. How would you solve the first?
Add three to the first.
Add 3 to both sides. We get p equals 3. And for our purposes, we don't know yet which one's extraneous or if they're extraneous. So I'm going to box in that answer. How would you solve the second one? Subtract 4 from both sides. So I get p equals -4. Again, I don't know whether or not that's the correct answer or not. It's what we're going to have to do here in just a moment. So we found 2 possible solutions. Now I know these 2 solutions would satisfy the quadratic equation, but were we solving a quadratic equation? No, we're solving a radical equation. So off to the right here, we are going to check for an extraneous solution. And our radical equation this time was the square root of 5p plus 21 was equal to p plus 3. Give you a second in case you're still jotting this down. So we'll start with the first one. See if 3 is in fact a solution. So I'll have the square root of 5 times 3 plus 21 equal to 3 plus 3. On the left-hand side, what would I do first? 5 times 3, which gives me 15 plus 21 inside the radical. On the right-hand side, again, that parenthesis is not doing much. So can I just go ahead and do 3 plus 3? So that gives me a 6. On the left-hand side, what is 15 plus 21?
Is it 36?
36. And what's the square root of 36? We get 6. So we end up getting that 6 equals 6. Is that true? Okay. So is 3 a solution? Yes.
Did you erase something?
I just erased, I fixed my highlight, my line. Then we still have to try -4. So same idea. So I'm checking to see if the square root of 5 times a -4 plus 21 equals a -4 plus 3. On the left-hand side, what's 5 times -4? -20. On the right-hand side, is that parenthesis really doing anything? No. What's -4 plus 3 then? -1. On the left-hand side, what's -20 plus 21? +1. What's the square root of +1? 1. So I end up 1 equals -1. Is that true? It is not. It's awfully close, but is close good enough? No. So what does that mean -4 is? Extraneous.
So in other words, that's what we're looking for.
We're really checking for that extraneous one, because what that means is although the -4 satisfies the quadratic equation, it does not satisfy the original radical equation.
So this was the way the answers are.
They're both answers. You didn't do anything wrong. By finding both, you didn't do anything wrong. But if you were to tell me that both were solutions, then I'd say, not so much. So I'm gonna highlight that word real quick. So your final answer would only be +3. Whew, look at all that. What a process. Still barely scratching the surface of math here though, so.
So you can see those giant, like those giant black tops or chalkboard that was covered. This is probably the most direct equation.
So it's really, when it comes down to it, it is a lot of steps, which is why I strongly, well before this, like from day one, I strongly recommended write neatly. If you write a little bit larger than someone else, that's perfectly fine. Grab some line paper, grab some grid paper, use as much space as you need to be as organized as possible. Because if I needed to go back during a step of this problem and see, what went wrong, I want to be able to follow my steps. And in theory, it would be a very boring exercise. I could start at the end of each of these problems and retrace where each value came from. Again, it wouldn't be fun. I wouldn't even have fun doing that, but I could do it, which means I could catch any mistakes if the answer I'm getting just doesn't seem to work. So I will be posting this video today. I'm also going to post this exact copy of the notes. The one I had originally posted in Google Classroom isn't as organized as this one. So even I get better more times I solve the problems. So, yeah, so that's it. If you have questions, feel free to either watch the video, check the notes that I'm going to post, or come chat with me.